Hello, everyone. It's my great pleasure to introduce Stefan Pelletier for today. Stefan was actually my first PhD student. So he started basically just after I arrived in Montreal. I still remember meeting him, and he was coming from McGill and super motivated. So we had a little conversation in one of the rooms at the old campus. And he convinced me to hire him. And it was actually a really great decision, as you will see today. So he's now at the end of his PhD. We're submitting the last paper for the PhD. He will be talking about his last two papers of his PhD. And it has been an incredible journey. So he really exceeded all expectations. Over these kind of 5.5 years, he got something like 12 or 13 PI proposals accepted. For all kinds of telescopes, from Gemini to the European telescopes, to James Webb, to everything. Today he will be talking about high-resolution spectroscopy. These are one paper accepted for Nature, published in Nature, and one that we're just submitting, also to Nature. So some really cool results that are kind of maybe the highlights of his PhD thesis. Yeah, what these observations do. These are not James Webb observations, but these are high-resolution observations. So in the era of James Webb, there's actually super exciting work to be done also from the ground for exoplanets. We had this initial idea like 5-6 years ago to dive into this high-resolution spectroscopy much more. I gave him initially a data set from Keck near spec. It wasn't so great, but it was a really great training set for him. Then we had some Spirou observations, and this is now from Gemini Marin X and from the VLT telescopes. And so you will see what we're doing. He really kind of did something for exoplanets that we can't even do for solar system planets.
Yeah, leave some for me.
I just want to give you an idea. Anyway, so that's, you know Stefan probably also because he brings all the good fruit and the apple and everything. So I'll let you present your work. Thank you very much.
Thank you, it's a pleasure. I just submitted my PhD thesis 2 weeks ago, so now I can finally sit back and relax and present some of the results. Now, I'll start with my favorite quote, which is in 1835, the philosopher Auguste Comte said, "En ce qui touche les étoiles, nous ne saurons jamais, par aucun moyen, étudier leur composition chimique." Oof, that feels bad. Now, obviously, that did not age well. We know the composition of stars and the sun very well. Here I'm showing the composition of the sun. So on the x-axis, the atomic number for all sorts of elements in the periodic table. And on the y-axis, we have the abundance relative to iron. It's normalized so that iron is 1. So this distribution of elements seems all over the place, but this is not like a random thing. This is the direct results from the Big Bang and billions of years of stellar evolution, nucleosynthesis, and supernova. And the end result is this. And this is the composition of the sun, but you look at other stars in the neighborhood, in the interstellar medium, they all have this composition. So this serves as like the building blocks of the universe. So if you want to build a star, you start from a big gas cloud, and then you just crunch everything up and form a star. So the reason that the star has this composition is that the composition you started with is what you end up with, because you just took everything and put it together. It's like if you ordered a build your own planetary system set at IKEA, very simple ingredients, very simple instructions. What about the planets though? Now that's a bit more tricky. Planets form in a protoplanetary disk, which is non-uniform, and it's a multi-step process. You have to first start with your solids, you have to build up a core, eventually you get big enough, then you go through gas accretion. So it's not really obvious that you would end up with the same composition as the star. So to further my IKEA analogy, if you buy a build your own planet set from IKEA, you might get a different composition or a different box ingredients, depending on where you are in the disk, and also different instructions. So one of the things we want to do is measure the end composition of a planet and try to chase back to which IKEA box we got. Now, planet formation is very complex, multi-step process, but we can break it down into the building blocks of planets, where we have gas, hydrogen and helium. Now, the nice thing about this is that throughout the protoplanetary disk, hydrogen and helium are always in gas form. Rocks, which is your, think of your normal rocks, your iron, magnesium, silicates. And the nice thing about them is that throughout the protoplanetary disk, they're basically always condensed into solids. And your ices, your carbon, oxygen, nitrogen. Now, contrary to these, which is already always in gas, and those who are always in solid, ices can be gas form or solid form depending on the temperature. The temperature varies throughout the disk. In the inner regions where it's warm, everything is vaporized. In the outer regions, it's cold, so everything is condensed. So these are the three main building blocks of planets. And basically, to understand how planets form, we want to measure the relative composition of these three components. Very simple. Now, let's start by doing this for the most obvious choice, Jupiter in our own solar system. So we've observed Jupiter and the other solar system planets with the most powerful ground-based telescopes that we have. We've sent the Galileo probe, which literally crashed into Jupiter with a mass spectrometer to measure its composition. And we have currently the Juno spacecraft, which is like $1 billion satellite mission that one of its primary goal is measure the oxygen content of Jupiter. Like, you know, measure one abundance on a planet, $1 billion, very expensive. So this is now the state of the art for the solar system planets in Jupiter. So you can see we have all of these measurements from Galileo and Juno. We have this nice Juno measurement finally after several years observing the planet. And from this, we've learned so much. This has guided the formation theories for how our solar system formed, not just Jupiter, but how it dictated how everything else in our solar system formed. But there's a problem. Do you see it? There's something missing. It's a bit more obvious if I plot them on a periodic table. These here are the elements that are measured that we've been able to measure on Jupiter. Notice they're all in the top right corner of the periodic table. Now, what's special about this corner? This is actually where volatile elements are. Now, what I mean by volatile is this thing that, like, at room temperature, like to be in gas form. So what's in gas form in our atmosphere? Your nitrogen, argon, oxygen, carbon. These are your volatile elements. But that's it. Why can we only measure this top corner of the periodic table for Jupiter? Because it's freezing cold. It's like minus 100 degrees Celsius on Jupiter or something. So all of your rock forming elements, we can't measure them. They're condensed. I'll give another analogy. If you have a boiling pot of water and on a really cold winter day, you throw it away, it'll just condense into ice. Same thing for Jupiter. If you take vapor of like iron and stuff, it'll just condense and sink to the bottom. So all of these elements here, we can't measure them. So we have this missing, like, it's hard to fully understand Jupiter if we have only a small portion of elements measured. Put another way, on Jupiter, we know how much gas there is, we know how much ice there is, but we don't know how much rock there is. So it's like a missing piece, like a missing one piece of a three-piece puzzle. So it's a large gap in our understanding that's missing. Which brings me to the ultra-hot Jupiter opportunity. So here I'm showing the clouds that are forming on planets as a function of temperature. You can see at cold temperatures, it's a nightmare. Like Jupiter, everything is condensed, even water is frozen, iron, all your rocks. It's hard to measure things when they're frozen and sunk to the bottom. But as you go to higher and higher temperatures, you enter basically close to the stellar regime. You know, in the sun, everything is in vapor form. That makes life so easy. Everything is in gas form. We can measure it from afar. So indeed, all these molecules and atoms that are condensed on Jupiter, on ultra-hot Jupiters, very easy to measure. Well, relatively easy. Which brings me to the first ultra-hot Jupiter I want to talk to you about today, WASP-76b. Now, this planet is very big. Like, it's the same mass of Jupiter, but it's roughly 6 times larger in volume. That's what it's because it's so hot. It's all puffy. And it's tidally locked like the moon around the Earth. It has one side always facing the star, which means you have a permanent day side being blasted by a radiation that's really hot. Like this is approaching the stellar regime. You'll have everything vaporized, you'll have metals, you'll have ions, and you'll have molecules being dissociated. Versus on the permanent night side that never sees the light of day, you can have a lot colder temperatures that are more traditional for the planetary regime. Molecules are stable, you can have condensation into clouds. And between these two extreme regimes, you have the terminator, which is kind of the transition between these two. And this is where we probe with transit spectroscopy, which is what we observed for WASP-76b, with Maroon X. So we used Maroon X on the Gemini North Telescope in Hawaii, very big telescope. Maroon X observes in the optical/red optical, so the light we see roughly with our eyes, has a very high spectral resolution, which means as a function of wavelength, you don't just get a couple of data points, you get super high resolution, you can resolve lines of everything. And we observe 3 transits, so when WASP-76 passes in front of its host star. Now, this is what the Maroon X data set looks like. So we take a spectrum and then another and another, and we build as a function of wavelength a time series. Now, the data contains the star, the planet, because we have to look through Earth observation. It has noise, Earth, and then the planet WASP-76 that we're looking at. Now, what you can see here, the dark lines, these are stationary in wavelength. This is fully dominated by the star signal and Earth's atmosphere. So we have these lines that are dark stripe fixed in wavelength that completely dominate the spectrum. We cannot see the planet here by eye, but there's a trick. The star and Earth's atmosphere are stationary in wavelength, but WASP-76, as an ultra-hot Jupiter with a very short period, it swooshes around its host star at very, very rapid speed. So like from 1 hour to the next, it will have moved a lot in Doppler space. So while the star and telluric lines are stationary wavelength, these would be angled. So we can run through data analysis detrending procedures to remove everything that is fixed in wavelength and keep things that change in wavelength. So if we did this right, we removed the Earth's atmosphere, we removed the stellar atmosphere, and we're left with just noise and the planet spectrum. Now, the noisier this looks, the better. We love this. And if I actually zoom in here, you can see something pretty amazing. You can actually see by eye the planet line. This is what I meant. This is here the planet line that's moving really quickly in wavelength, and it's only here occurring during transit. The observations had bad weather at the start, but they started right when the transit started, and then at the end, when the planet finished transit, the absorption stops. Now this is cheating. This is like the strongest line you'll ever see on a planet. So normally things are not that easy. And so what we typically do is we have our data and then we generate a model. And when you're not so lucky that you can see a line by eye, we do a cross correlation. So this is a calcium plus line, and this has like a really strong triplet. What we can do is just cross correlate data and model, and then some things some along the time axis for different orbital configurations. So we might not know the real planet velocity. So what we do is we do a blind search. We cross correlate and then we sum along different axes of Kp and Vcis, which basically are different lines in this graph. So we try different solutions, which give us points on this graph. And then eventually we'll get something that matches the signal, which will give us this. So this is our classic results plot. It's not the most like physically meaningful, but it's a nice, pretty figure. You get a nice big blob of white at the center. It's very visually pleasing, which is why I like them. So we repeated this cross-correlation process for a whole bunch of different species, molecules, anything we can think of. We generated a model, cross-correlated, and generated this plot. And we were able to find all sorts of elements, 16 in total, on WASP-76b. So we have like iron, which just pops out like super strong. sodium, calcium plus, chromium, and a whole bunch of other ones. Of particular interest to us was actually this VO, this purple one, vanadium oxide. This was really surprising to us. People have been searching for this molecule for like the last 15 years, and it just kind of popped out right away. This is actually the first time that it's been seen at high resolution, unambiguously on an exoplanet. So that was really cool. Now, you might have noticed, like, hang on, you have like a cross, and then a lot of your detections are kind of offset from the cross. Like, what's up with that? And indeed, if you zoom in, I have this cross here, and then this signal, and it's offset. What's going on here? So the cross is actually, this is what we would expect if the planet was uniform and had no winds or nothing. So you have a very boring planet that's symmetric with no winds. A signal is expected to be where the cross is. And obviously here we're offset. So to fully understand why the signal is offset, we have to go back all the way to March of 2020 for an event that changed all our lives. No, I don't mean the COVID shutdowns. I mean the discovery of iron rain on WA76b. La presse, pluie de fer sur une planète lointaine. Le temps, il pleut du fer sur l'exoplanète WA76. So this was their press release, WA76 singing in the iron rain. And this was their kind of money figure that showed this effect. So here is the radial velocity in the planet frame as a function of time during transit. Now, what you need to know is that the signal should be straight at zero. And obviously it's not straight at zero. It kind of goes leftward and hangs around leftward. Anyways, long story short, they interpreted this as iron rain from the planet. You have kind of one side of the planet that's hotter and another side where it rains out, which is why you, at the end of transit, you don't see portion at zero. You only see some on the left, which is blue shifted. So you have one side of the planet that has no iron and another one that has some. So it must rain out of the atmosphere. And we're actually able to confirm these results with our Maroon-X observations, where here we have the equivalent plot, the Doppler shift in the rest frame as a function of phase. And you can see we would expect normally a line at zero, and clearly this is not a straight line. This is kind of a curved line that hangs out left. But interestingly, this is just for iron. So what we did is, for all of the other elements that we detected as well, we did the same plot, and we noticed that the other elements also show this curved pattern. And the other elements, they have all sorts of different condensation temperatures. So this theory that iron rains out of the atmosphere, it seems to not work, because then you would expect different behavior for different other elements that have different condensation temperatures. So our results showed that the cause of this effect is much more likely to be a global process, where instead of rain out, you still need a planet to be asymmetric, but for different reasons, where maybe you just have one side that's a lot hotter or one side that has clouds. But we can't really distinguish between those two scenarios. Anyways, we've digressed. I'm talking about dynamics and stuff. We wanted to measure compositions. So we ran through atmospheric retrievals, and we were able to actually get abundance measurements for all of the planets. Here it's the abundance relative to iron for all of these elements, sodium, potassium, lithium, and so on WA76b. Okay, there's just a bunch of data points everywhere. This is kind of meaningless, but it makes more sense if I overplot now the composition of the sun. Remember, our building blocks of the universe. Now we can see that, okay, it's kind of following more or less the trend. If you look in the middle, you actually have quite a good match between WA76 and the sun for manganese all the way to calcium. Here, on the other hand, you have a mismatch. You have these three that are underabundant, apparently. And these are actually the alkali metals. What's special about alkali metals? They're all the way on the left end of the periodic table. They only have one valence electron, which means they're very easy to ionize. And this is an ultra-hot planet. So we think that actually this makes sense. These three are underabundant because they're more easily ionized than the other ones. And on the other side, we have the solar composition, which predicts a lot. And on WASP-76, like we don't see any of these elements. They're completely absent, and we can constrain their abundance to be like orders of magnitude depleted. And these are actually the ultra-refractory elements. This will make more sense if I plot now as a function of condensation temperature. So now I'm showing, again, the relative abundance, but normalized to solar. So 1 is solar, above is supersolar, and below is depleted. And all of the elements that I talked to you about that are mostly following solar, sure, we have some deviation, but they're not completely way off. And then all of a sudden, once you reach elements that have a condensation temperature more than like 1550, bam, all of a sudden, like you're completely depleted. So we seem to have a very, very sharp transition where you have all of these elements in gas phase on WASP-76, and then poof, you have certain elements that are completely absent. So this was a really interesting finding. And what we're now wondering, and this is hopefully what we'll figure out in the future, is what happens if you would take WASP-76 and heat it up a little bit? Would titanium, bam, all of a sudden become apparent? And what happens if you just instead cool it down a bit? Would calcium disappear, and then barium disappear, vanadium disappear? And what's leading us to think this might be happening is that here we have WASP-76, iron very strong, titanium species completely absent. Now, if we look at another planet that we recently published as part of a collaboration, this is another ultra-hot Jupiter, but it's a bit hotter, like 400 Kelvin hotter. You still have the iron, but now titanium, titanium oxide, titanium plus, bam, all the way, all of a sudden they're there. So what we've been building up with these proposals that I've been submitting and in collaboration with Vivian Pelletier is, here we have just the space of planets as a function of radius and temperature. All of the planets that have names, we have observations or planned observations. And what we're really looking to see is, are there these, like, are these sharp transition general for planets, for ultra-hot Jupiters? So here's WASP-76, here's WASP-189 that I showed. So these have titanium, this has iron. Now, where does this transition occur? And is it really that sharp? And then if you go lower, does the iron disappear all of a sudden? So you might have two planets that are very similar in temperature, but have completely different atmospheres. So that's one of the things we'll hopefully figure out in the coming years. Okay, so that was conclusion part 1. So we observed WASP-76b, an ultra-hot Jupiter with Maroon X in transit. We detected a whole bunch of species, 16 in total, including the first high-resolution detection of vanadium oxide. And we were able to measure the composition of all of these elements and figure out that they're actually quite solar all the way until there's a sharp transition in condensation temperature. And now we're looking forward to see if this behavior is universal on other ultra-hot Jupiters. Okay, now before I move on to part 2, I can take questions if anyone has them, and if not, I will just move along right ahead.
Are differences in velocities between species significant?
Some, yes. So actually, different species, like I showed you calcium plus, which has a crazy line that you can see by eye, which means we're probing super, super high in the like exosphere, while other elements are probing the more hydrostatic atmosphere. So you can have different dynamics in different layers of the atmosphere. So I kind of glazed through, but yes, you can actually have different offsets for different elements, and they more or less follow which layer of the atmosphere you're probing. Okay. Oh, sorry.
Correct for the
yeah. So I kind of just wanted to blast through this, but indeed you have this dark band here is where there's actually iron and all of these metals in the star atmosphere. And so you can have contamination. I tried to correct it, and you can do a pretty good job, but I figured it's just safer to just mask out all of this region and ignore it so that you don't risk contaminating your results. So that's why there's kind of a portion of the data that we just completely ignore. Okay, now coming back, Jupiter, we saw, has all of these elements measured in this top right corner of the periodic table, which are volatiles, so ice-forming elements. And now we observed WAS-76, and we measured all of these species that are in gas form in its atmosphere. And these are actually all refractory, so rock-forming elements. Now, it's kind of annoying, but they're basically all on this side of the periodic table. What we would want to do is actually to bridge this gap. We want to know the relative amount of ices and rocks. We don't just want one, we want both at the same time to get this full picture of how planets form in terms of gas, ice, and rock. So to do this, bear with me, but now I have a different ultra-hot Jupiter. It's very, very similar, but it's just a bit better. It's a tiny bit hotter, has a shorter period, so it's a slightly more favorable, but for all intents and purposes, it's just another ultra-hot Jupiter that's roughly the same as WAS-76, but it's the WAS-121. Now, this time, we observed it in emission. So the last time I observed WAS-76 with Maroon-X was when it transited its star. Now we're actually looking at WAS-121, where it's kind of behind its star, and we see its day side. So we're actually looking at the full hemisphere of the planet. And we're looking at its thermal emission rather than stellar light filtered through its atmosphere. And we observed it with the CRIRES Plus spectrograph. This is work that I did in collaboration with Romain in this room. And we observed it with the espresso spectrograph, which is an optical spectrograph. And this was work that I did in collaboration with a professor in Sweden that I went to visit to do an internship as part of a CRAC international research internship. So this is infrared observations, and these are optical observations. And the reason why we need to combine these different regimes is that, really annoyingly, the refractories all have opacity in the visible light, while your volatiles, your molecules, tend to all have opacity in the infrared light. This makes sense when you look at the stars in the night sky with optical light. You can see the stars. So there's like no water absorption blocking our light. But try looking at the star in the more in the infrared, and you won't see anything. So it's kind of this dichotomy where if you look at the optical, you'll just only see the metals. And then it's the opposite in the infrared. So we have to really use two different wavelength regimes, merge them together in order to get both. Now, I won't bore you with all of the data reduction techniques. I'll just skip right into the results. Now, here we have the radial velocity of the cross-correlation function, which is colored, as a function of orbital phase. And here you have in the middle the eclipse. This is when the planet goes behind its star. So we observe the planet before and after eclipse. And this dotted white line shows kind of where we would expect the planet to be from a priori assumptions. And then you can see this white line. You can actually see the planet signal go through. Like you can see it by eye. This is pretty crazy. You can just see the planet follow its orbit. So we're pretty happy with that. Now, and one thing to notice is that the light that we see is actually in emission. So often when you look at colder planets, you'll see signals that are in absorption, but here it's in emission, which is indicated of an atmosphere that's thermally inverted. We'll come back to see that in a bit. Now, looking instead at the classical plots that I showed you that are just visually nice to look at with a nice blob, we can see we detected carbon monoxide and water. These two are with the CRIRES Plus observations in the infrared. And then we also detected iron with the espresso observation in the optical. And I'll actually note that these detections for carbon monoxide and iron are kind of centered to where we would expect them to be. But if you look closely, you can actually see that water is a bit offset, which might hint towards kind of an asymmetric distribution of water on the planet. But that's still work that we're looking into. Now, we were able, like I mentioned, these signals are in emission, so we're actually able to retrieve the temperature structure on WASP-121. And you can see here, it's colder. Here it's temperature as a function of pressure. It's actually colder deeper in the atmosphere. And as you go higher and higher in the atmosphere, it actually heats up. And here you can really see the difference. I've been talking about ultra hot Jupiters. You've probably heard about hot Jupiters. What's the difference? Well, if I actually compare to what a classical hot Jupiter or boring hot Jupiter would be, a normal hot Jupiter would just have a temperature structure that decreases in temperature with altitude, while an ultra hot Jupiter would have increasing with altitude. So that's kind of the difference. But focusing on WASP-121b, this is what we retrieve. And what's crucial to note is actually that the temperature structure is hotter than the iron condensation curve. So if you're kind of to the left of this line, iron will tend to condense and form clouds. So like Jupiter, you know, is like here or something. Not that much, but so crucially, we're on the right of this curve. So this is why we see iron in vapor form. But you would not be able to do this on a colder, even hot Jupiter. And another nice thing is that we detected water, carbon monoxide, and iron. And here's like the contribution function of these species. This is basically where in the atmosphere these species probe. So water in blue actually probes deeper in the atmosphere, and then iron in green actually probes higher in the atmosphere. So having these multiple detections allow us to probe different regions of the atmosphere, kind of get better constraints on its temperature profile. And our results actually match well with previous HST observations, which kind of, this shaded region is what they constrained, and we're more or less consistent with them. And we're actually nicely consistent with just model predictions. So in pink, we have a one-dimensional model prediction, and in orange, we have a GCM prediction. And we're actually like more or less following what the models predict, which had me scratching my head at first. It's like, wait, data that matches the model? That can't be right. I must have done something wrong. Anyways, so this was the temperature structure, but again, I digress. What we were focusing on is the composition. So we're actually able to measure the abundance of elements in WASP-121b. So here I'm showing the iron to hydrogen ratio. So here is the rock to gas ratio, a proxy for this. And this is just the posterior we retrieved in white. In blue, you have the solar composition. In red, you have the stellar metallicity. And then in white is what we measure. And we're actually consistent with two other works that also measure this value. So this is pretty boring. The planet matches the iron to hydrogen ratio of the star and of solar. Boo, boring. But now what is interesting is when we go through and measure the ice to rock ratios, so the carbon to iron and the oxygen to iron ratios. Now you see that the stellar and solar composition in red and blue were actually to the right of these. So we're actually, the ice to rock ratios are actually superstellar and supersolar, especially for carbon to iron. In the sun, you might have 10 carbon atoms for every one iron atom. But on WASP-121b, we're more like 100 carbon atoms for every iron atom. So that was quite interesting. And we're also enriched in oxygen, although not quite as much. So this is a complicated plot. I'll just simplify it. If you have to take this kind of the take-home message a bit, is the rock to gas ratio on WASP-121b is stellar, but the ice to rock ratio is superstellar. So that's already interesting, because these types of measurements, like we said, we can't even see for Jupiter. So these are like among of the first types of constraints we can get on giant planets. So it's quite interesting that they seem to be ice rich. Now, we have this composition. Now, what does that mean? Like, what can we tell from this about formation? Here I'm showing a protoplanetary disk where planets are believed to form. You have a hot protostar in the middle, so the temperature of the disk decreases in temperature as you go radially outwards. And this means that the disk will have these different snow lines, we call them. So in the middle, everything is hot, so everything is vaporized. And then the soot line is past which carbon can condense. And then the water snow line is past which ice can condense. And same thing for CO. To give you an example, within the water snow line, you'll have rocks, but your water will be in gas form. But past the snow line, it's too cold, so now your water will condense and stay in solid form as solid ice. So we can actually predict the composition of the planet. Remember our IKEA sets. We can consider 8 different formation locations within the soot line, between the soot and water snow line, close to the water snow line, and so on. So we have 8 different formation locations in the protoplanetary disk. And for each of these locations, we can predict if WASP-121b formed at this position, what composition would it have? So this is work that I did with Yayati Chechan, who's a postdoc at McGill. And he ran these models and he's like, okay, for all of these different positions, I will predict, these models predict these abundances. So here we have the iron to hydrogen ratio normalized to the stellar value. And here we have the oxygen to iron. And in this parameter space, these different lines predict which the composition of these different locations. So depending on where our results match here, it might indicate where WASP-121b formed. So our results lie here, and like seriously, I think it touches every single line within the 3 sigma limits. Like, so we're like consistent with absolutely everything. WASP-121b can have formed everywhere in the protoplanetary disk, when we only consider iron to hydrogen and oxygen to iron. But we also measured carbon. So actually, when we add in the carbon measurements, we get these 2 other spaces. Now, what we're looking for is lines that cross our posteriors in all 3. And we actually see that although everything crosses here, in these 2 other scenarios, there are actually only 2 lines that cross our posteriors. So if we trust everything here, then we can actually rule out 6 of our 8 considered scenarios, and we can conclude, or at least what our results indicate, is likely that WASP-121b formed either in scenario 6 or 7, which is near the CO snow line. So you would have basically CO enriched material, either in solid form or in gas form. So yeah, just to repeat that, WASP-121b, from our measurement, seems to have a metal-enriched atmosphere that's volatile rich. So it's a stellar composition in rocks, but it's a superstellar composition in ice. And what this means is likely that WASP-121b formed far out in the disk and then later migrated towards its current position very close to its host star. And actually its orbit is misaligned, which kind of indicates that likely it was dynamically kicked to where it is today. So to conclude, we observed WASP-121b with CRIRES Plus and Espresso, and then we were able to detect carbon monoxide, water, and iron in emission. We were able to measure the composition of these elements, iron, carbon, and oxygen. And we found that the iron abundance, so a proxy of the rock to gas ratio, is stellar or solar. And then the ice to rock ratios are actually superstellar. And from this, we can conclude that WASP-121b, a giant planet, probably formed with more ice than rock, and likely that this means that it formed further out in the disk. Yeah, so that's it. Now, but before I finish, I want to do a shameless advertisement plug for apple picking. If you guys want to bring your families or friends to apple picking, you can come to my orchard. We're actually doing a UDM Apple Day this Saturday. So everyone's welcome to come, and yeah, I'll even leave you drive the tractor like René did last year. Thank you.
All right, Stefan, thank you so much. Other questions?
In the second planet that you look at, the emission, how can you disentangle the emission from the planet and the simple reflection from the star?
Yeah, that's a good catch there. Because indeed you'll have the stellar spectrum, which will reflect on the planet, and if it has a decent albedo, it will reflect and appear as if it's coming from the planet. Probably that this could be a contamination only at short wavelengths. So we expect as you go to longer wavelengths, the infrared light dominates. But if you were at very short wavelengths, it's possible that the reflected light could play a component. Ultra-hot Jupiters and hot Jupiters somehow seem to have very low albedos. So we don't think that this would be a problem. But also just from the modeling, this planet, like even when you model it, the thermal emission dominates in the wavelength regime we obtain. But you could have some contamination, but it's probably at like the below 10% level.
In your first part, +76 the condensation of species seems to be occurring in the 1500 day, right? So, but the temperature of the planet itself is hot. So, what do you tell about where this condensation?
Yeah, indeed. So, we're talking about ultra-hot Jupiters, and I showed temperatures of like over 2000 Kelvin. But the condensation temperature is normally around 1500 Kelvin. So your condensation doesn't actually occur on the day side of the atmosphere, but on the night side, which is a lot colder because it's like tidally locked, never sees the light of day from the star. It's very cold there. So you can actually have your iron and your other species, they condense on the night side, and then it kind of depletes the day side. So you could have kind of a cold trap mechanism that just gets all these metals that are stuck on the night side. So when I talk about condensation, I mostly mean night side condensation. And then you can have a transition region, but yeah, that could be kind of more complicated.
So when you compute the C to the carbon to iron ratio, do you do it only based on the CO and H2O abundance? Do you expect to see another part in the bonded atoms?
Yeah, that's a very good point, which is something I kind of skipped over, but I'm measuring the iron abundance, and I'm relating this to like the rock to gas ratio. What this relies on is that when I measure the iron abundance, it fully represents all of the iron. But like there could be iron condensed out, there could be iron that's ionized. So that's something we have to be careful about. In this regime, this is actually a nice regime in the ultra-hot Jupiter. It's like a cold ultra-hot Jupiter. I know that that's a weird name, but like for iron, at least, we're in a regime where most of the iron is expected to be in neutral form, and you're only expected to be ionized at high altitudes. Now you asked about carbon. Same thing applies for carbon and oxygen. When I measure the carbon to iron ratio, where does this carbon come from? In our measurements, we measure CO. So the assumption is that when we measure the CO gas abundance, that it represents all of the carbon in the planet. Now that may sound like a big assumption, but that's actually what the chemical equilibrium predictions are. Like at hot planets, just the carbon loves to be in CO. So when we measure the CO, it should be well representative of the carbon abundance. But you also asked about oxygen. Now that's a trickier one because some of the oxygen is in carbon monoxide, some of the oxygen is in water, but at these temperatures, water can dissociate, which is actually something I kind of skipped over. But when we actually, here is the volume mixing ratio of the species we retrieve as a function of pressure. We can actually see that the water favors to be quite dissociated. And then this can create OH and atomic oxygen. So if we don't get this right, then we might kind of get the oxygen abundance wrong. And I'm not claiming that this is a perfect solution, but basically we're probing the water abundance deep in the atmosphere where it should be well representative of the bulk abundance. If we were probing higher up, then we would need to take into account atomic oxygen and OH, which is not included in this run. But we tested our results by running a retrieval that includes chemical equilibrium that takes into account this dissociation of water and OH and atomic oxygen, and we get very similar results. Yeah, here you might look at the signal seems to be favored here and then kind of doesn't really appear here or here. This is not necessarily physical. It's just because these observations are actually 4 different observations. And the observations are kind of split between like here and here and here. And basically here there are 4 nights of observations, while here there's like only 1 night that covers these phases, and here there's also only 1 night that covers these phases. So like here we're actually getting like, 4 times the observing time as here or here, which is why it just looks stronger there. But good eye.